Okay, in this problem, we have to address several questions related to this integral here, or actually to this family of integrals, right, which depend on a parameter k, which is going to be a natural number, right? All right. The first question that we need to address is whether these integrals converge for every k. Actually, we have to prove that they do, right? Well, this is an improper integral in both extremes, so actually, to address that we have to deal with two integrals, not just one, right? You have to deal with the integral from 0 to infinity, okay, and then the integral from minus infinity to 0. And we have to assess the convergence of both of them, right? But actually, we're going to see with a simple change of variable that this integral here is essentially this one, right? So assessing the convergence of this is enough to conclude that both are converging. And the reason for that is, if you look at this here, and this is the answer to A, right? If we make a change of variable, which is just t equal to minus x, so dx is equal to minus dt, right? Then what we have is the following. We have the integral when x minus infinity t is plus infinity, when x is 0, t is 0, and because of this minus, we can swap the limits of integration, so we can write the integral from 0 to infinity and compensate for this minus, right? And then we have minus t to k here, and here we have e minus t squared dt. All right, well, minus t squared is just t squared, and this one is just this constant, minus 1 to k, the integral from 0 to infinity, tk e minus t squared dt. So you see, essentially, up to a constant, this integral here is just this integral here. So all we have to do is to deal with this first integral, and then we have the answer to a problem, right? So let's focus now on this, on the fact that this integral converges. Okay, we have this integral, right? T to k. Well, actually, I'm using the variable x, so let me just keep the variable x. Doesn't matter, the name of the variable is irrelevant. And what we're going to do now is another change of variable. This time, the change of variable is taking x squared equal to t. Just to get rid of this x squared here and put just a simple exponential, right? So x is equal to t 1/2, and therefore dx is equal to dt over 2 t 1/2. Okay, now limits. When x is 0, t is 0. When x is infinity, t is infinity. Then we have x to k, and that is to k divided by 2. Then we have this, another power, minus 1/2, right? Because this is in the denominator. We have a 1/2 here. And then we also have e minus t dt. Okay, we have here an integral that we have discussed several times in theory and in problems. This is the integral from 0 to infinity of this decreasing exponential times t to a power. It doesn't matter what the power is, well, as long as it's positive, because this involves 0, but k is a natural number, so the smallest value this can take is 0, right? So this is either 0 or a positive power. Then this integral is converging. All right, we have proven, just for clarification, we have proven several times, or we have used this fact several times. We have proven in theory that this integral here is convergent, right? For any alpha, it's convergent for any alpha real, positive or negative, doesn't matter. What I'm saying now is that if you include a 0, then you have to be careful, because this integral, if alpha is negative, is not only an improper integral because the upper limit is infinity, but also is improper at 0 because t to a negative power is divergent, right? And in that case it's different, right? In that case, actually, it is only convergent if alpha is larger than -1. Okay, only in this case, right? So, but there's no problem in our case because, as I said, the exponent is always going to be positive, which means that we don't have any problem at 0, right? So it's positive or 0, so we can forget about this, right? But you have to be careful with this, right? The lower limit is important because this, no matter whether the exponent here is negative, this limit is, I mean, the behavior of this function in this limit is regular, perfectly regular, no problem. However, if you extend it to 0, then and the exponent is negative, then this function is singular, and then you have to assess the two separately. So you have to divide this into this integral plus this integral. This integral, there's no problem, converges for any alpha, but this one, for this one, alpha negatives can make a problem. And actually, it's only convergent if this happens. Okay, this is a side note. For our case, in our case, we don't have that problem, and we know that this integral is convergent, so ik converges for any k, a natural number. Now the second question is, we have to calculate the integral for k odd, but that is very simple. Actually, we have already done it here. If k is odd, what you have is the integral, and this is the answer to B, the integral of x to k e minus x squared dx, right? And as we've seen here, this decomposes into the integral from 0 to infinity xk e minus k minus x squared, and then this plus this constant times the same integral. But it turns out that this constant is negative if k is an odd number, so what we have is this tk e minus t squared dt. You see, this integral and this integral are the same, so this is 0. So actually this is the same symmetry argument that it holds for integrals, for ordinary Riemann integrals. If you know that this integral is convergent, since the interval is symmetric and the argument or the integrand is an odd function, the integral has to be 0. Actually, this is the proof. What we've done here is just the proof of this. All right? And similarly, if k is even, which is the next question we have to answer, if k is even, then we can replace this integral by twice the integral from 0 to infinity. Okay? Right. All right, so that answers the problem for k odd. The answer is this, just this. And now we're going to focus on the case that k is even, right? And for this case, we have to devise or to derive a recurrence for this integral here, right? And that recurrence allows us to calculate any of these integrals if we know I0. I0 we are not able to calculate it, but I've told you several times that this is something that you will get in Calculus 2. You will learn how to calculate this. So let's take it for granted here. And what we're going to do is, if we know this value and use the recurrence, then we can derive this formula. That's the last step. We can derive this formula to calculate the value of I to n, right? Okay, so let's do that. So let's derive first a recurrence for I to n. I to n is just the integral from minus infinity to infinity of x to n e minus x squared dx. Okay, the standard way of deriving a recurrence is using integration by parts, right? And in order to do that here, what we're going to do is to deal with this function, which is the most complicated one. We can't find the primitive of this, of course, but if we had here if we had this function multiplied by the derivative of this, then there will be no problem, right? The derivative of this is 2x minus 2x times this, right? So that's the derivative of this function here. So all we need in order to complete the derivative here is 1x, but we have plenty here. We can use 1 for this, and then a constant, right? But that's not a problem, because we can introduce a constant and divide by the constant. Actually, we can do this, right? And then the integral from minus infinity to infinity of, as I said, you steal 1x from here, and then what you have is minus 2x e minus x squared dx. Okay, this minus 2 is compensated by this minus 1/2, and this x is the x that we have stolen from this x2n here. There's no problem, because the lowest value this can take, and is any natural number, is n equal to 1, and this is still a positive exponent, so perfect. We don't have any problem. We can do this. Now this is the derivative, right? This is the derivative of this exponential, and we can integrate this by parts. Actually, as I said, well, okay, let's integrate this by part. So we have minus 1/2, then we have this function x2n minus 1, then we have this exponential, and then we have the limits, which are these two limits. And we have to add, well, we have to subtract, but since there is a minus here, we have to add 1/2 the integral of the function e minus x squared times the derivative of this function here, which is 2n minus 1 times x2n minus 2, okay, dx. All right. Now, what happens to this function when we take the limit x to infinity? Well, because of this function here, it goes to 0. And that's the same if we take the limit to plus infinity to minus infinity. So actually, this is equal to 0. So what we have here is this. We have this constant, 2n minus 1, divided by 2, right? And then we have the integral from minus infinity to infinity. And we have this power and this exponential. And if we compare this with the original integral here, we see that the exponent has changed, but that's the only thing that has changed. So we have exactly the same integral, right? But with index 2n minus 2, which is now the exponent that you see here. And this factor here, you can divide term by term. 2n over 2 is n, and then we have minus 1/2. So that is the recurrence that we have found. So we found that I to n is equal to n minus 1/2 times I to n minus 2. There you go, right? Okay, now we can apply, and that is the last question, we can apply this over and over to calculate integrals. So for instance, if we want I2, what we have is, well, n is equal to 1. So 1 minus 1/2 is 1/2, so we have 1/2 I0. If we have I4, that would be n equal to 2. So the first factor is here, 2 minus 1/2 is 3/2, so we have 3/2 times then I2, but I2 is 1/2 times I0. If we want I6, then is this n is equal to 3, that is 5/2 times I4, which is 3/2, 1/2 I0. And that continues this way, right? So if you have I to n, see what you have here, you have 1, 3, 5, all the odd numbers. The next one is going to be 7/2, etc., right? So you have all the odd numbers starting from 1 below this, which is 2n minus 1, 2n minus 3, etc., times 3 times 1 divided by, you have 1, 2 factor for each one of these, and that is 2 to the n, y0. Okay, or you can write it like this, or you can write it dividing every factor by 2, and then you have n minus 1/2, n minus 3/2, etc., 3/2, 1/2, 1/2, sorry, 1/2 times I0, which is the square root of pi. And that is the formula that appears right here. Okay. By the way, there's a way of writing this. As you can see, this is the same as the factorial, but only that you're jumping from 2 to 2 by 2, right? So you take 2n minus 1, then you jump, you skip the next one, and you multiply by 2n minus 3, and so on. So you are multiplying the even or the odd, depending on which one you start off from, right? There is a symbol for that, right? You can write this like this. It's 2n minus 1 double factorial. Double factorial means that you are skipping one factor. Okay, so you multiply by every other factor here, okay, until you reach 1 or 2, depending on the one you're starting here. So that's another way of writing the same result, okay? If we had started with 2n, so 2n double factorial would be 2n minus 2, 2n minus 4, etc. times 4 times 2. Okay, that is the same thing. So it's a new definition of factorials that you can use, but you can also leave it like this. All right.